Okay, so we've got 8.3 part 2, so we're going to be doing examples 3 and 4. Example 3, graphing natural base functions. So the basic function is y equals a times e to the r, and then x minus h. H will indicate any kind of a horizontal shift, plus k. K will represent a vertical shift. But the base function is y equals a to the rx. Okay, so for part A, it says graph the function, state the domain and range. So my function for A is y equals 3, which would be my A, e to the 0.4, 0.4 would be the r, x. And this does not have a shift because there is no h, there is no k, so because a is positive, and r is positive, the function is an exponential growth function. So we plot points. So 0, if I plug in 0 for x, so if I plug in 0 for x, that's going to take 0.4 times 0 is 0. E to the 0 power is 1, and 3 times 1 is 3, so 0, 3. And then if I plug in 1 for x, 1 times 0.4 is 0.4. E to the 0.4 power, I have to do on a calculator, so if I do e to the 0.4, so e to the 0.4 is equal to about 1.49, and then we multiply that by 3, and we get approximately 4.475. So we'll just go ahead and round that to 4.5. Close enough on this size graph. Okay, so we have 0, 3, and we have 1, 4.5, so that would be right about there. Okay, and it's exponential growth, and it has no vertical or horizontal shift, so that means that we have it's going to have the x-axis is my horizontal asymptote. We're going to approach that from the left, so we start close to it but not touching it because we don't touch our asymptotes, and we curve it up. Okay. The domain is all real numbers because I can plug in whatever I want, so all real numbers. Okay, and the range is all positive numbers. Okay, or all positive real numbers, because that boundary, the horizontal asymptote, is at y equals 0. So that means that my range is everything greater than 0. Y is always greater than 0. Okay. So my next one is for B, y equals e to the negative 0.6 times x plus 3 minus 2. Okay, so this time I have an h and a k. So if I look in the parentheses next to the x, I have x plus 3. Well, if it's in the form x minus h, that means that my h is actually negative 3. And my k, because it's in the form plus k and we have minus 2, that means that my k is negative 2. So that means that I'm going to have a horizontal shift of negative 3, and I'm going to have a vertical shift of negative 2. I'm going to go ahead and raise this up here really quick. Okay. So I start by graphing the basic function, the y equals e to the negative 0.6 x. Okay, and I look at those. Well, a is positive because a is 1. My coefficient on e is 1. So a is positive, and R, my rate, is negative 0.6, so R is negative. R is negative. Okay, that means that the function is exponential decay. So I translate the function of y equals e to the negative 0.6 to the left 3 and down 2, because my h is negative 3, so that's a left 3 shift, horizontal shift of negative 3, and down 2, because my k is negative 2. I'm going to go in the vertical direction, negative 2 units. Okay, so let's do the y equals 1e to the negative 0.6x first. So that would give me the base function. Okay, so the original function would be 0, comma, and then if I plug in 0 for x, negative 0.6 times 0 is 0. E to the 0 power is 1. 1 times 1 is 1. So that would be 0, comma 1. So this is my original function. Okay. If I plug in 1, okay, so if I plug in 1 times negative 0.6 is negative 0.6. Okay, if I do e to the negative 0.6, that gives me approximately 0.5488, and then if I multiply that by 1, I get 0.5488, of course. So that would be 1 comma, and we'll say 0.55 is close enough. So 1 comma 0.55, so just above the halfway mark, but just barely above the halfway mark. And so then remember, this is my base function, so it's approaching the x-axis. Okay. However, my new function is shifted 3 units to the left, so 1, 2, 3, and 2 units down, 1, 2. So that means one of my points is right there at negative 3, comma, negative 1. And then my other point, if I shift over to the left 3 and down 2, okay, is going to be at negative 2, comma, and then I have to take 0.55 and subtract 2. Well, 0.55 minus 2 would be negative 1.45. So that's why I've got this right above the mark there. Okay? And so it follows the same basic shape, however, but it's been shifted down to that, so that means that my new horizontal asymptote is over here at y equals negative 2. And so my actual curve looks something like this, and I approach, but I don't touch the asymptote. So my domain is still all real numbers, because I can plug in anything for x that I want. Okay, but the range now is everything greater than negative 2, because I've shifted down 2. So y is greater than negative 2. Okay, now move on to example 4. Okay, so now example 4, finding balance in an account where we've got continuously compounded interest. Okay, so compounded continuously. So this is where we use E instead of our normal formula. So our formula for finding the account balance after some period of time is A equals P, the initial principal, times E raised to the R, which is the interest rate, times time. Okay, so in the setup, we have a deposit of $1,400, which is our P, into an account that pays 4%, which is our R, and we want to find the balance after 1 year, so that's our T. So P equals 1,400, R equals 4%, which is 0.04, and T equals 1 year. So the balance A equals PE to the RT. All I do is plug in 1,400 times E raised to the 0.04 times 1. Well, 0.04 times 1 is 1. E to the 0.04 power is approximately 1.0408. And then if we multiply that by 1,400, we get approximately $1,457.14. We round to the nearest penny because we're talking about money. Well, back in example 4 of lesson 8.1, we found that the balance from daily compounding, so that is we compound the interest at the end of every day, we got $1,457.13. So continuous compounding earned us a whopping 1 penny, $0.01 or 1 cent. Okay, and that takes care of E, the natural number. So we are now done with 8.3, all examples.